All right, thanks everyone for coming. I hope you enjoyed the conference so far. I certainly did. Especially the boat ride yesterday evening, that was quite awesome. So, since I was a kid, or when I was a kid, I wanted to build a time machine. So, I don't know, I had this obsession about building a time machine, and so my father said, son, if you want to build a time machine, you have to learn functional programming. He didn't really say that. He's a math teacher. He probably would have said that I should learn category theory. But a bit later, you know, this movie came out, Back to the Future. Could I have a show of hands who knows the movie here? Most of you, that's great. If you don't know the movie, watch it. It's awesome. And I thought, wow. I really got to have a flying DeLorean someday, and you know. And now, some years later, I'm working with the Java virtual machine, which, you know, it's a great thing, the Java virtual machine, but I have to admit it's not as cool as a flying DeLorean. But, you know, it's good enough for data migration, large-scale data migration with Akka, and this is what I want to talk about today. So let's get started. I will start by giving you an introduction to what this project was about, how it came to be, and the story basically. Then I will go and do a bit more theory, futures, actors, and pipes. And I think the most interesting part will be the lessons learned part, where all the fun stuff comes in action. A few words about myself. My name is Manuel Bernhardt. I'm a freelance software consultant and I live in Vienna in Austria. I'm a member of the Vienna Scala user group, which is a pretty awesome group. We have 198 members, so we're waiting for 2 more, and we make a big party. I'm mostly working with web-related projects from the front end to the back end. And for the past 5 years almost, I'm working with Scala, Akka, and the Play framework. I also started writing a book on reactive web applications. It's going to come out, or the MEEP is going to come out in 1 month or something, if everything goes according to plan. Okay, so let's start with the background story. So this is a story of a startup that's called Talenthouse. They're based in Los Angeles with offices in London, Berlin, Munich, and Mumbai. And what they do is they connect artists and brands. And they also have quite a few users. So this is what you get when you go to the front page of Talenthouse. You get a picture, pretty cool, nice. And this is all art that comes from the community. If you log in, you get to see these campaigns. They're called creative invites. And their brands can say, listen guys, we need help with designing, for example, a short movie video for Spotify. This is the brand says, we need your help. And then artists can go in there, submit their movies, whatever they come up with. And then there is a voting part where people vote using Facebook and Twitter. And at the end you have a sort of voting, and then the winner gets a money prize or a car or, well, whatever. It really depends on the sponsor. So why did they have to do this migration? It's because they had a system that was written in PHP and it was slow and it wouldn't go any faster. It was developed by an external company, which made the communication a bit more difficult. And so they looked around and they said they were going to insource the development and we want to do it with Scala and Play. So they contacted me and they had a pretty tight schedule to do all of this, so it was 3 months' time they had set as a target to rewrite the whole thing and migrate the data. So for us, for the data migration part, which is what I want to talk about here, is the source system is interesting. And before I talk about the source system, I just want to say a few words. I'm not here to bash the people that created the system. Because it always happens, you're in a project, the goals change, so something, sometimes when you get on the project and you're thinking, what the hell is going on? I think this was, we all know this kind of situation. I just want to put this here as a little disclaimer, because it's going to look like I'm bashing them now. So we start with the Zen framework in the middle, and then Amazon SimpleDB as a non-relational database, NoSQL database. And basically what people can do, and on this platform they can fetch stuff from pretty much anywhere. So here are some examples, but there were quite a few more cloud services from which the users could upload artifacts or link to them anyway. So metadata would mostly be sent over and stored in SimpleDB. And all of this was running on Amazon Web Services with Redis in front to act as a cache when there was a lot of traffic. Otherwise it wouldn't be fast enough. Then, I think what happened is that they thought our data is more suited for a relational database after all, so let's move it there. I think that was the plan. What actually happened is they didn't manage, so this is what happened. And then, as I got to know the data, I figured that quite some fields, like description or text, instead of having a value in there, they had a link to a .json file stored on Amazon S3. And if you looked at that JSON file, you didn't have JSON in there, that would be too easy. You had JavaScript in there that would evaluate to some data eventually. But you wouldn't see any of this when you looked at the source code. You wouldn't see any of this in the front end. So I think what happened is this. That's sort of a node server or something that kind of evaluated the JavaScript in the back end. But I have no proof of this, so I call it a pirate Node.js server. So at this point, it was already a bit, you're like, geez, I'm gonna have to. If this looks familiar to you, you may have seen this. This is sort of how we felt like when we sort of discovered what was going on. We only ever had access to the databases and not to the system itself, so we didn't even know the source code or anything. We had to just figure everything out of the database. There was no MongoDB, luckily, and there just two databases was enough. So then we had this thing with the migration schedule, where basically the idea was, on a Friday evening, we turn off the old site, and on Sunday evening, we switch on the new site, and in these 2 days, or nights and whatsoever, all the data is migrated over, right? That's cool, huh?
And you end up in hospital.
Yeah, something like this, yeah. So, big bang, and we also tried to do incremental migration beforehand, but it was not always possible. We'll see why. So, that's when we decided to go for something pretty awesome for this, which is Akka. I'm going to go in the part where I talk about futures, pipes, and actors a bit more in theory. And I will start with futures. So a future is a box that basically stores a value, and it's eventually going to have this value, or it will fail. So either it fails, either it succeeds. A short example, not a very, it's quite a dumb example, doing 1 + 1 here. So this will hopefully print 2 in the console when you run it. So that's easy, that's cool. Now if I do something even more stupid, like dividing 1 by 0, this won't work, as you can imagine. And there is one thing here, if I want to get a result printed when I run this code, I have to actually block. So don't do this at home. I mean, if you really have to, you need to block, but here we will see right away why we need to do this in this case. But when you run this code, you get this nice exception here that you shouldn't do this stuff. Dividing 1 by 0, it doesn't work usually. And if you want to handle this kind of exception, so this is just an example, but the kind of exception, you have to add a recovery mechanism here. Be mindful, so you sort of know this might throw something, so I can deal with it. And when I run this code now, I will get, what on earth are you trying to do? So why do we need to do this await? Why do we need to block here explicitly? When you use futures, the exceptions are propagated up the chain if you compose them. If nobody will call for the future explicitly, it will sit there and nothing will happen with the failure. And that can cause quite some despair sometimes, especially when you're not used to it. So always think about recovering at some point, because otherwise you will not notice when things fail. There's a cool thing you can do with futures, which is composition. So for example, here I have two futures, and then I have a for comprehension. And in this for comprehension, I have two branches, one for each future. And these two futures will run in parallel. They will run, so with 1 plus 1 and 2 plus 2, it's not going to be very exciting. But if you were to do, for example, some HTTP calls, something that takes a little longer, then it's useful to have this run in parallel. And at the end, you get everything goes together in an addition here. You could say, oh, I want to do this shorter and write this. And this is not a very good idea, because what happens is that futures start running from the moment where you declare them. So here, when I declare them, they start running. If I declare them only here, they will run wherever I declare them, and so it means this for comprehension will run in sequence. Another thing about futures that you can do, I don't like it so much, but it's useful. You can add callbacks, success or failure handlers. I don't like it so much because it mutates your future, and I don't like mutable stuff. It makes it harder to reason about the code. But when you use Java, you can use Scala futures from within Java, and when you use these callbacks, it's quite cool. That's a neat way of integrating it. About using futures, if you have a future block and you only do CPU-bound computation, that's not a very useful thing to do. Because if you only do non-blocking code, then why would you need to use a future? So another thing you might want to do is to use the right execution context. So if you, for example, have an application that does a lot of blocking database calls, you may want to use a separate execution context with a separate thread pool in there for this purpose. And finally, a thing I learned recently is when you have blocking operations, you can actually tell Scala, or the future API, that there is a blocking block. So this looks like this. You import Scala concurrent blocking. For example, here we have a typically, we call some SQL database with JDBC that's blocking. And if you use this blocking thing here, this one, it will actually tell the execution context, this part of the code is blocking. And then it can do more, it can be smarter about it. And also it's a good documentation. When you read the code, then you see explicitly, well, this part is blocking. One last thing about futures, naming them. So this is something.
Wait, this is not from Back to the Future?
Yeah, this is. If you have a future of an option of a thing, you have a type. It may be enough to have the type. You don't have to do a long Hungarian notation. I don't know how to call this way of calling a variable name. If you eventually make a string, that's a very nice prose, but I personally can't see this anymore. It's like you repeat yourself, just use the type. But you know, that's my taste, so you may disagree with it. Okay, let's talk about actors. Actors are lightweight objects. You can have millions of them in memory, in the JVM. The Akka team always comes out with crazy statistics about what they do to their poor MacBook Pros before they burst up in flames and under the load. These little objects, they send messages to each other. They communicate with each other, and they have a mailbox in which they receive messages, and then they handle them in the order in which they receive them. And actors can have children, so this is a kind of a supervision principle, and they're really responsible for whatever bad things their children do. If they crash, They have to sort of decide what happens. It's a very useful thing if you want to have a fault-resilient application. So for example here, I have George Peppard and Audrey Hepburn playing Breakfast and Tiffany, and there's also the cat, and Audrey is responsible for the cat. And then, they send each other messages, and they can reply, don't have to reply. And what you will notice here, you have this URLs. So this is the actor reference. And the actor reference is like a phone number that you can use in order to reach an actor. So if you want to get an actor, you first have to extend the actor trait here, up here, and implement the receive method. We'll see, we will look into that in the next slide. Then we have an actor system, which is where all the actors live. And at the end, we ask the actor system, please actor system, I want an instance of an Audrey Hepburn actor. And then you don't get an actor itself, you actually only get the phone number, the actor reference. So then if we want to send and receive messages, we implement the receive method. It's a partially applied function, the receive method. And so you can pretty much pattern match whatever you like. Case classes are, in my opinion, the best thing you can put in there, or case objects. It's just a single command without parameters. And that sort of describes the protocol that you're going to build. So in this case, we have a script where there is some text for the script, and then Audrey, when she receives it, she can read it. This is how you send a message. You say Audrey, bang, script. This bang is the exclamation mark here. It means tell. And it's a fire and forget operation, which means that you send it off and you don't care anymore, you go away, it's sent. Sometimes you may want to get an answer, so then you use the ask pattern, which is where you're going to sit there and wait until you get an answer. But when you do that, you may want to specify, or actually you have to specify a timeout. How long are you going to sit there and wait for an answer? Here Audrey has just 1 second to answer. And what you get is a future. So you don't get an answer directly, but you get a future, and then you get to deal with this future. Yeah, it's called ask. Quickly, supervision. So here we have an example that comes from the user migration part of the data migration pipeline we had. It's a simplified example. The user migrator was the guy running over all the users in the old system and sending them off to a few children. So for this, you sort of initialize an actor context, which is the thing you use in order to get, for example, to initialize child actors. And here we want 100 of them, and we're going to use a thing called a router, which is going to decide how the message is going to be sent to the children. And we use a round-robin router. The round-robin router is this, the very old pre-LAN kind of networking style where you have a circle and one message gets to each actor in the circle. You see my awesome drawing skills here, or not even drawing, just using tools. So you have the user migrator, the router, and then all of the child workers here that will get the messages. You have another part of supervision, that's the supervisor strategy. If you have a child that is misbehaving or crashing, you have to decide how you're going to deal with it. So you may use, for example, here the one-for-one strategy, which means that for each actor that crashes, I'm going to do only something with that one. You also have the one-for-all strategy. There's no all for one, not one for all. I'm getting confused with the D'Artagnan kind of mousquetaire thing here. But mainly there you say, I want just one actor to feel the consequence of it crashing, or I want to restart everybody because of that guy that crashed. So that depends. Here we just set it up with 3 retries and we restart after having logged that the child has died. So the next thing, and that's been quite useful to us during data migration, is pipes. A pipe is an Akka pattern, just like tell and ask, and it's useful to combine futures and actors. So what it does is quite simple. It takes the result of a, you plug it into a future that lives inside of an actor, or outside, but you plug it into a future, and when that future will has completed, the result will be sent to the actor you give it to. So here we have a simplified example of one actor that was doing file fetching. So it gets up here, it gets the order, fetch the file at the following URL, and then we download, we initiate a download with this WS library from the Play framework. This call is asynchronous here. We just grab the response in a downloaded file. We get all of the bytes here, which is super cool because you get all of the bytes of the file in memory. Don't do this at home, or do it when you know what to do. And then here is how you use the pipe. So you say download, which is a future, pipe to original sender. So two things here. Why this original sender? As said, this download code here will run asynchronously. So if you download a 3 GB file, the actor may get another message that asks it to download something. And if you call the sender method when the download is finished, you may get the reference from another guy that sent you the message while the other one was downloading. So you will end up sending the answer to the wrong guy. So this is why we capture it here. Then, this is just a thing you should always do, is kind of use case classes. Don't just send raw types around, because otherwise you will end up being confused in your API when you get raw types. It's always good to have the protocol always defined. Now, will this work? What do you think? Yeah? No? Well, it depends. When everything goes well, it works. But when there is something like a URL can't be found, or the file can't be downloaded, or your network just died, you will have a problem. So, which is why at this stage you should be careful and recover your future. If you don't recover, Akka will still send the answer over to the actor. But it will wrap it in an object called Akka actor status or status, and it will only capture the exception. It won't have any context. You will get an exception, but you don't really know what to do with it because you don't have any context. So always think about this part. So in summary, futures are tools to do a bit of low-level manipulation of asynchronous operations. Actors are a good way to organize complex asynchronous flows, and pipes are a way to deal with futures inside of actors, or outside of actors if you need to, but they're really useful inside of actors, I would say. Now to the more interesting part, the lessons learned. The first thing is about how to design your actor system for migration. Always know your data. So for example here, we have a simple setup wherein you have a user migrator, which will go and talk to the source database, fetch all of the actors, and send them off to child workers. With Amazon SimpleDB, we had a maximum page size of 2 megabytes, so we kept on polling and paging over the database, and as soon as we got the results, send it off to the workers. So that worked well in this case, because it was a pretty straightforward setup. With the user items, so each user could have items, the first design we had was like this very nice supervision thing, where you have the item migrator comes here, fetches all the, or goes through the users, sets up user item migrators. They're responsible for migrating all the items of one user. And this user item migrator was having 2 workers, or more than 2 workers, I don't remember exactly, to handle the migration of one item. Now the problem with this setup was that not all of the items, not all of the users had the same amount of items. So that some users had hundreds or thousands of items, and some users had no item whatsoever. And in this case, this kind of setup is not very efficient. So what we ended up doing here is another approach, wherein the migration workers were set up, and all sorts of other kind of actors that we were using. You see but a few of the different types of actors we had were set up in pools. So depending on what you needed, you were using these actors in this pool, and that way worked out much better. And that way as well, we had more control as to how fast this whole thing could run. Because eventually we had to run it, right? And we did the first test run 3 weeks before the launch. And I did that at 11 a.m. Central European Time, which is about 3 in the morning or so in Los Angeles, I think. And then this is what happened. So we basically busted the live system. So the London office called Daniel, the CTO in Los Angeles, which then told me to stop. So that's the lessons learned number one, I would say, or one of the important ones is if you deal with a legacy system, be gentle. It may be, I mean, especially if you're there and you're like, yes, I have Akka, I have all the power, and you're like, yes, I want to be fast, and then it might just be too much for your legacy system. So just be gentle, right? And then the next thing is always use cloud APIs that implement the following ISO standards, because then you're going to have a much easier time dealing with all sorts of things. You know, you always get the same response codes, you always get the same timeouts. I'm messing with you. That's not what happens. What happens is you're in the Wild West. Good luck. For each and every different cloud provider, they're going to have their own error codes. They're going to have their own response rates, their rate limits, etc., etc., etc. So don't even try to deal with them. You're going to discover what happens. There's one interesting thing here is about rate limits. When you get banned because you went too hard to one API. So for this, you know, you can read the documentation and hope that they're going to document how much requests you can do in a given time window. And what's important here is you need to design your actor system, or the whole migration system, so that you can take into account these limits. Otherwise, you will have your IP banned, and that's not good. Also, keep track of the migration status. Because if it stops midway, or if you're banned or something, it's good to be able to resume and not have to refresh everyone, if you can. I think some people from SoundCloud are here, right? Yeah? So, I mean, this was frustrating, right? So, with SoundCloud, up until 3 days before the weekend, we kept getting 500 internal server error messages randomly. We didn't know, it was not after a certain amount of requests. It was not after a certain time. It was just random. And I sent a mail, I think, to the support. I sent a mail to some mailing. I think it got lost somewhere there. And then, it was getting closer and closer to the weekend. And then I did something I never do. I went to Google. Oh, I do that. I went to Google, and I had my query. And when you scroll down in Google and you have these little numbers called pages, and I clicked through them to pretty much one of the last one. And then I found an archive entry from some arcane mailing list. And there I discovered the magic user agent. So when you were giving foobar as a user agent, suddenly all the 500 internet server. So I don't know. It's it's this kind of.
It's fixed now.
You
should fix now.
Sorry.
Right? I'm working on it. Right now. I'm fixing it right now.
So yeah, this is one of the fun things, one of the many fun things you get to discover. I mean, I have a lot of more stories, but I'm not going to bore you with all of them, but they're fun. This kind of project is inspiring and fun. All right, so let's move on here. Blocking. You're like, maybe I'll block here, just in this small part of the application. Maybe just here, if I block, it's going to be fine and nice and yeah, no, it's not a good idea. So you block just in one thing, and then sure enough, after some time, like after 8 hours of running the migration, sitting in front of the screen, the whole thing goes to hell and runs out of memory because you're blocked. So don't block. It's a bad idea. You will end up rewriting the code asynchronously anyway. We have the tools for it. It's fun. You get better and better at it. So just don't block. One more thing here. Some random things. So this cron job. You remember the cron job that went both ways in the source thing? Yeah. So what happened is that we noticed when doing this migration incrementally beforehand that suddenly some users in the new system had the double items or triple items than in the old system. So what happened is the primary IDs of users and items would change, which is that's maybe specific to this situation, but this is something you never know what can happen. That's my message here. You never know how the data will look like. So one thing I found to be really useful is to not try to build a big migration pipeline, but rather chop it into little pieces and make as many tools as you can to do this kind of data quality control. So there is this tool called SBT tasks, if you don't want to learn how SBT works, which lets you really easily add new commands to the SBT console. And we use that to add tools to migrate little, just one user or just one item, or delete all the items of this guy, or delete the whole user, resynchronize them, generate a report where in Excel to see what's, how many items in the old system, how many in the new system, things like that. So this is quite useful. Okay, so I think that's it, but we'll always have Paris. Thank you. Good. Do you have any questions? Yes?
Yeah. Did you use some stuff to control the flow of actor and how to...
The flow control to see how my messages were going, passing around? No, I didn't do that because it pretty much worked. I mean, I pretty much knew because I was the only one working on this on the system, so I had a pretty straight image of how my system was functioning. So I didn't really use that. Yeah?
How do you throttle the speed of migration and the level of parallelism? Is there any tuning for both?
So in this design, so first we could control the number of actors in one pool. So reducing that pretty much helped already, because then you can just, for example, for Cloudinary, or for SoundCloud at the end, I had just one guy there, being gentle to the API, because I didn't know what was going on. Cloudinary, which is an image API, also has a rate limit on concurrency. So they detect how many connections you have open with them. So you couldn't have more than 3 at the same time, otherwise they were stopping. So, I mean, these pools of actors, that's a pretty cool thing to do. There is another thing that I used, I call it the poor man's back pressure, is that when we were pulling things from the database and sending it off to the workers would always acknowledge when the one user was finished, for example. So I always knew in my controlling actor how many items I had in queue, sort of, or in pipe. And then when it got to a too large number, I would just sit there and sleep, which is not the nice things of doing it, but it works. It's why I call it poor man's back pressure. Shouldn't do that, but for this kind of application, which is not that, it's not a constant production kind of thing. It's this one-time thing that you run. So, fine. Okay. Yeah.
Did you use a default setting for Akka, size for Akka?
Yeah. I didn't try to, because after running it the first time and the whole thing going to hell anyway, I didn't try to optimize much more. Yeah, SoundCloud?
Yeah, what do you use if you use something to monitor your actions? Like, do you know any monitoring solutions besides not so much over there?
Monitoring for Akka?
Yeah, like what's going on?
There was a type safe.
Did you ever need to maybe?
Well, in the system, I was the monitor. I was sitting in front of my screen and watching the logs. That's what I did for a long time during the initial phases. This weekend I set my eyes were completely destroyed, but I didn't really have the need in this project. Are there tools, do you know, are there any use?
There are tools like New Relic and App Dynamics, Canon, but all have different trade-offs. So, I guess you have to ask a specific question. They all kind of help you to monitor. Typeset itself doesn't have any. We have a tool called Inspect with Activator, but it's more development time.
And go ahead.
Okay. Do you know what was the exact cause of the out-of-memory exception that was the result of blocking?
So there was this one cloud provider that dealt with video files,
Okay.
and I had looked in the database and there were not that many items with video. So I thought, let's just block in here. And then, sure enough, if you block and then these files or this whatever state accumulates and all these messages weren't handled fast enough because these were large files that were not hosted on AWS, so you had to ship them over and that would take time. And then at some point it was too much to move. So. More questions? Or?
Yeah, so about the ask method.
Yeah.
How would you send back the message like from the actor view? So if you ask for something, you get a future, right?
Yeah.
What about the actor you're writing? How does it respond? Does it only send to the sender and it automatically matches the question?
The ask pattern, how does it get back to the actor, or?
Yeah, how the actor responds to an ask instead of a tell.
There is no difference. You always get a message of a certain type.
Yeah.
But in this case, the ask pattern, you get always a message and then you answer to it. So it's just the part that will ask for it that has to handle this timeout there. That's one part that didn't show you in code. It would be a good thing to show is that when you specify a timeout and then you do an ask, and you will get an exception if the thing runs times out. So that's one place where you need also to handle the.
Okay. But then the actor side just sends the sender back information. Right?
Exactly. You use the sender reference to send back the information, which is on the first example. I can go back to that very quickly somehow. Yes, this one. So you capture the sender when you have a future. Otherwise, you can respond directly. And then you just answer, well, this is an example for pipe, but you would otherwise be able to just send an exclamation mark. But this is because you have a future, that's where you use the pipe tool. Yeah.
And if you have an actor communicating to another actor, do you use ask or do you use just tell and then the sender gets back to respond?
The best practice is to use tell all the time.
Oh, okay.
And you keep in track who asked you. So in the end, I ended up with, I think, a protocol of 80 or so different case classes. And most of the response case classes had always the reference. And sometimes it was 3 or 4 levels of interaction because, you know, this would go here, then this would go here, then this would go there, and then further and further. And you always need to go back to the chain. That's what you need if you want to have correct error handling and a good log, which is useful.
Thanks.
Okay, well, if there are no more questions, thank you very much for coming.